Okay, moving on here. Now we come to space-time diagrams, part 1, as we mentioned in the last video clip. This is a way to visualize how events occur. And we'll find it's very useful later on when we're dealing with some of the concepts of the special theory of relativity. But let's go back to the key concept from the last couple of video clips, and that is a grid or lattice of clocks. That is our observer's system here. So that, in this case, again, we're just doing the x-axis, one dimension. So we have a clock at every single point along the x-axis that we're interested in. And we will assume that all those clocks are synchronized using a method like we talked about in the previous video clip. And here's our observer again at the origin. So what we want to do now is really think about a series of events that occur. So we might, again, imagine some flashes of light, little strobe lights go off or something like that. And what we've done here is specify the x and t coordinates of these flashes. So we'll just use time 0, 1, 2, 3. We'll assume seconds, say. So at 0 seconds, 1 second, 2 seconds, 3 seconds, we're going to have, in this case, 4 flashes. At time t equals 0, we'll have a flash that occurs at x equals 0. At time t equals 1, we'll have a flash that occurs at x equals 1. Time t equals 2 occurs at x equals 2. Time t equals 3 occurs at x equals 3. So if we were creating a little movie or animation of that, it might look something like this, where okay, at time t equals 0, according to these clocks, which are all running just fine here. So we'd have a flash of light there. 1 second later, we'd have a flash of light here, and then a flash of light here 1 second after that, and a flash of light here 1 second after that. So we get a series of flashes. Each flash is recorded on the clock that's at that point. So again, our photo clock principle, or the clock principle, that's what it means to observe an event, that we take a photograph at that point, and we know what the location of that clock is, and then we know what the time on that clock is, and we say, oh, it can be very specific in terms of when that event occurs, that flash of light in this case. So physically, again, we're just looking at the x-axis here. We're just looking at events along the x-axis. Technically, you could say these flashes actually occur right on the x-axis, but we're sort of expanding it a little bit here. So that's what our observer would see. You could go back and check the photos generated by the clocks when those flashes of lights occurred, and you could say, hey, at time t equals 0, there's a flash at x equals 0, time t equals 1, a flash at x equals 1, and so on and so forth. Now, here's where we get into the new visual representation, the so-called space-time diagram. So what we're going to do is draw it down here first. Eventually we'll bring it up here. It's a little easier to work with, but I want to keep this on here to remind ourselves this is physically what's going on. We're just looking at motion in one dimension along the x-axis. We could expand this to 3 dimensions if we wanted to, but it's a little messy that way to draw, certainly, and also to see what's going on. So 1 dimension, and I'm going to reproduce the x-axis down here. So something like this. And we'll get the tick marks about the same. And by the way, I hope you're taking notes as we go along here. Use the provided handouts. Use your own notebook if you like, because as we mentioned before, just that process of taking notes, writing it down, helps it stick in the brain a little bit more. So let me make sure I've got this roughly the same here. Yeah, when I'm off to the side, it's hard to get the angles right or the distances right between everything. So I think that's more or less good enough. So minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so this is our x-axis again. All we've done is just reproduce this one down here. A little tilted, but I think it'll work. And now we're going to add a time axis. Okay, and we're going to do it right along here at the origin. Time there. And do 1, 2, 3. We'll do 3 on it. 2, 3. Okay. So essentially we're creating a plot here. Okay, so remember back, maybe dredge your mathematical memory a little bit if it's been a while since you've done these things. And we're just going to plot these events on this t versus x plot, time versus its x location. So that each flash here, we'll use orange for our dots, say, to represent the green flashes here, just to make sure we realize this is not the physical representation that we'll see here, but it's representing the physical reality up here. So at time t equals 0 and location x equals 0, we have a flash. So that would be right here. We'll do a little circle there. I don't want to get too much black ink on my nice orange marker here. And then at t equals 1, at time equals 1, I have a flash or an event at x equals 1. So at t equals 1 here, x equals 1. There's another event. At time t equals 2, this flash right here, the third flash occurs, and that occurs at x equals 2. So at t equals 2, I've got x equals 2 right here. And finally, I have the fourth flash occur at x equals 3 and time t equals 3. And so it occurs right about there. Okay? This one we could fill in a little bit. So those are the 4 points on our space-time diagram. It's called a space-time diagram because we have space represented along the x-axis, time represented on the vertical axis here, the t-axis. And so it allows us to do space-time events, space-time plots, as it were. Okay? Because I had 4 events there that occurred here, 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 here in succession. On the space-time diagram, this is what it looks like. At t equals 0, it occurred at 0. T equals 1, I had 1 there. T equals 2, I had 1 there. T equals 3, I had 1 at that location. Very important not to get this mixed up. We're going to use these a fair amount. And sometimes when you start looking at these, you imagine, oh, this means the flashes are going up at some angle. In actual fact, no. The flashes are just going along the x-axis here. This is the x-axis. This is the time at which the flash occurs. And in fact, sometimes it's useful to imagine a little stop-motion animation or something that maybe you've done once upon a time. And each time slice here at time t equals 0, this is a photograph of the x-axis. And at time t equals 0, there's an event, a flash that occurs right there. And then imagine at time t equals 1, in fact, let me use mine. So at time t equals 0, if we could take a photograph along the whole axis, that's what it would see. And then a little bit later, at time t equals 1, it'd see a flash at x equals 1 there, right there. And then a little bit later in time, you'd see a flash at x equals 2. And a little bit later in time, you'd see that flash at x equals 3. So you can imagine a sort of strobe light type thing, a strobe there, and then 1 second, 2 seconds, 3 seconds. So again, the actual flashes are not going up at some angle. They're going just along the x-axis. But when we do the space-time diagram, then we represent it as this upward going line. And in fact, we could, if we want to be nice about it, we could even draw sort of a line through there like that to represent that series of events, especially if we had a whole bunch of other events in between there that followed that line. Another way to think about this, going back here, is what if we had a car or a spaceship or something traveling in one dimension along the x-axis. And as it travels along, it gives off flashes of light as it's going on. So as it's traveling along, when it hits time t equals 0 here, flash of light there. And then a little bit later, flash of light here. All right. And then a little bit later, flash of light there. And a little bit later, flash of light there. So really the flashes of light record the progress of our spaceship or car or whatever it is along the x-axis. And again, this then represents the line itself here, when I connect the dots, represents the path of that spaceship or car through space and time. So again, a space-time diagram. And what I want to do now is just do a few others here so we can start getting a sense of using the space-time diagrams. So let's just change up our numbers over here. We'll use t equals 0, 1, 2, 3 as before, but let's just change the x locations of these flashes. So now we'll assume there's a car or spaceship going along and giving off those flashes of light. And so let's put some new ones in here. We'll just do, say, 0, 2, 4, 6. Okay, so again we'll leave these here for a month. This was case 1. Now case 2, at time t equals 0, I have x equals 0. So again, a flash of light occurs there. So we'll do, okay, flash of light, t equals 0, x equals 0. Next flash of light, which occurs at t equals 1, occurs at x equals 2. And then there's one at x equals 4 and one at x equals 6. Okay? So at time t equals 1, that flash occurs at x equals 2. So it's way over here. So I've got a flash of light here now. And then at time t equals 2, it's going to be x equals 4. So about right there. I think I've got that, maybe not a little bit higher there. Sorry, messy point. And then at time t equals 3, it occurs at 6. So 3 over here to 6, something like that. I'll clean that up a little bit. I don't know. Anyway, okay. So in this case, again, if this represents a car, spaceship going along, its flashes there, assuming it's moving at a constant velocity here, so it's not changing its speed, its velocity, or anything. Then we could draw a line here, more or less through those points. Okay, and that would represent the space-time progress of that car. In fact, we have a special name for these lines that we're drawing here. They're called world lines. World lines. If we imagine the car's progress through the world, as it were, in space and time, the world consisting of both space and time, in this case just space along the x-axis, one dimension, and the time recordings there. This represents its progress through space and time. We call that a world line. Okay, so there's another example. Let's do another one here. We're just essentially changing where the flashes are occurring each time. So for this one, let's do, say, -2, -1, 0, 1. Okay, so now, and you might actually pause it and do that plot and see what you get here. And then we'll come back and see how we plot it here. So we've got t equals 0, a flash at -2. So here's our first flash, second flash at -1, third flash at 0, and fourth flash at 1. And so if we were to plot those now, the x-coordinate we've got t equals 0, -2. So it's actually over here. Again, I don't want to mess up. Get too much black on a nice orange marker again. So there's 0, t equals 0, it's at -2. At t equals 1, it's at -1. So here's time t equals 1, and it's -1 there, more or less. And at time t equals 0, it's at 2 right here again. And at time t equals 3, it's at 1. So right there. And so then its progress looks like this for that case. Okay. Note that these two lines are actually parallel to each other, but just moved over here. In other words, this one, the series of flashes started at 0, at x equals 0, at time t equals 0. This series of flashes started at -2 over here. But its progress was the same. It moved ahead one segment on the x-axis each time. Okay? And actually, let's just do one more to demonstrate something. So in this case, let's do 0, 1, 4, 9 for our flashes. Okay, so this was the case where the 4 flashes in sequence occurred at -2, -1, 0, and 1. Again, that's the physical reality. This is the space-time diagram. This is the world line if that was a car or a spaceship traveling along with those flashes there. So now let's do the flashes here. At time t equals 0, it's at x equals 0. So we have a flash right here at x equals 0. At time t equals 1, x equals 1. So another flash here in sequence. Then at time t equals 2, it's at x equals 4 now. So it's up here. And at time t equals 3, it's at 9, so 8, 9. So it'd be out here someplace, roughly speaking. Okay? Note that if we were imagining a car or spaceship there traveling along, it seems to be accelerating. In fact, it is accelerating. It's going faster and faster. Our flashes are not equally spaced here. You know, it's slow, and then this time, in the next second, it jumps to here from 1 to 4, and the next second after that, it jumps from 4 to 9. So clearly, it is actually accelerating. And if we were to plot that on our plot here, we're going to get rid of this one so it doesn't get too messy here. Okay, so let's plot that. Again, go ahead and pause if you like and do your own little plot. It shouldn't be that difficult to see, but good thing for the brain. Just let it sink in there a little bit. And so at time t equals 0, x equals 0. So we're here again. Time t equals 1, x equals 1. So it's really this point right here. Time t equals 2, x equals 4. Okay, so time t equals 2, we're at 4. Actually, this one. So in fact, just to distinguish them here, let's draw green circles around to indicate this case. So there's that one, of course. It was at 0. And then at t equals 2, it's at x equals 4. And at t equals 3, it's at x equals 9, which would be here someplace. So right in the middle of our world line thing. Something like that. And if we were to draw a line through that, it looks something like this, roughly speaking. Okay? Well, not quite like that. Hard to draw that. Point being is it would not be a straight line. It'd be a curved line. Okay? And when we get into more of the details of the special theory of relativity, we will find that we will only be dealing with constant velocity situations. That things like this where we have a curved line, where something is actually accelerating. So when you see a curved line on a space-time diagram, whether it's curving that way or curving up, it's an accelerating situation. And as we'll learn, the special theory of relativity does not apply to accelerating situations. It only applies to constant velocity situations. So just wanted to mention that because you might ask, well, why are we doing examples where everything's straight? Well, the reason we're doing examples where everything's straight is that's where the special theory of relativity will apply. But this is the concept then of space-time diagrams. And in the next video clip, part 2 of this, we're actually going to look a little bit more closely at the concept of velocity and what that means in terms of these world lines, or what these world lines really mean in terms of the velocity of an object, say like our car or spaceship, going along and giving off flashes. On to space-time diagrams, part 2. What we want to do here is explore the concept of velocity as it's represented on a space-time diagram. Let's just remind ourselves here what a space-time diagram is. We actually have 4 cases this time. So we're going to imagine that we have our spaceship or car traveling along the x-axis. And it's going to give off flashes at certain points in time. And of course, we have our grid or lattice of clocks all along the x-axis at any given point, so that when that flash occurs, a photograph will be taken and it will record the location of that clock where the photograph occurred and the time on that clock. And all the clocks along the x-axis we will assume are synchronized using a method that we reviewed in a previous video clip. So, got our spaceship. We're going to imagine 4 trips now, 4 passes or 4 runs of our spaceship along the x-axis. And all of them will start at t equals 0 and x equals 0. So they'll all be starting at the origin here. We don't have to do that, of course. We did an example where we started at someplace different than the origin, but for our purposes here, we'll just always start at the origin, t equals 0, x equals 0. And then we've got run 1, run 2, run 3, and run 4. So let's just review what's going on there. So run 1 starts at x equals 0, then at t equals 1, it's at x equals 1, t equals 2, x equals 2, and so on and so forth. And that is this space-time diagram here, or this world line right here. Remember, the world line represents the path of an object through space and time. And so at t equals 1, it's at position 1, x equals 1. At t equals 2, it's at position 2, at t equals 3, it's at position 3, and so on and so forth. So this is the world line for run number 1 of our spaceship as it's traveling along the x-axis. You'll probably get sick of me saying this, remind you of this, but this is not, the spaceship is not going up at some angle. The spaceship is constrained to move only in one direction along the x-axis. We'll assume it's moving in the positive direction. It could move the other direction as well, but only one direction, back and forth along the x-axis. All our examples here, it's moving just to the right in the positive direction. So that's run number 1. Then we reset things and come back, and it starts another run. At t equals 0, it's at x equals 0, and then 2, 4, 6, 8. So it's at t equals 1, it's at 2. At t equals 2, it's at 4. At t equals 3, it's at 6. And at t equals 4, it's at 8. So that is run number 2. And this is the world line of our spaceship in run number 2. Run number 3 goes at t equals 0, again, starting at x equals 0. Then t equals 1, 1/2, and then 1, 1.5, and 2. So at t equals 1, it's at 1/2 here. At t equals 2, it's at 1. T equals 3, it's at 1.5. T equals 4, it's at 2. And we will assume that we have clocks, in between here at every single point that we need. And then the fourth run, just to do something different, we'll assume it's actually moving in the other direction now. So it starts at 0 again, but then goes at time t equals 1, it's at -1, and then -2, -3, 4. So at time t equals 1, it's at -1. Time t equals 2, it's at -2. Time t equals 3, it's -3. And then at time t equals 4, it's at -4. Okay, so 4 different runs of our spaceship. Now, let's remind ourselves about the concept of velocity. We probably all sort of know it, depending on how much you've done things like this. You may not have thought too much about it, but we know that velocity is distance divided by time. Distance covered divided by, say, elapsed time. Okay, distance divided by time, right? Miles per hour, kilometers per hour, feet per second, meters per second, and so on and so forth with that. So how does that relate then to our diagrams here, or our world lines here? Let's take the first one, number 1 here. Run number 1. Just looking at it, we can say, well, we went we'll just say we're using meters here. So we went 1 meter in 1 second, and then we went 2 meters in 2 seconds, and then 3 meters in 3 seconds, and 4 meters in 4 seconds. Pretty clear we're going 1 meter per second. But if we want to calculate that, we could say, let's just take the 3 here. X equals 3 in 3 seconds. 3 divided by 3 is 1 meter per second. Or 2 divided by 2 is 1 meter per second. And because it's a straight line, as we talked about before, that's a constant velocity situation. And we're going to use that in just a minute. Let's look at number 2, though, which is this one here. Note that in 1 second, we're going 2 meters. So the velocity at that point, or over this distance here, would be 2 meters in 1 second, 2 meters per second. Or we've got 4 in 2 seconds. 4 divided by 2, 2 meters per second. Or 6 in 3 seconds. 6 divided by 3, again, 2. And so on and so forth. 8 divided by 4 is 2. So velocity in this case would be 1 meter per second. Velocity in this case is 2 meters per second. Velocity in this case, again, because it's a constant velocity, we're not changing the velocity. We can just pick any given point and read it off. But we've got 1/2 meter in 1 second. So it's 1/2 meter per second. If we did 2 meters in 4 seconds, 2 distance divided by 4 seconds, 1/2 again, 1/2 meter per second. And then the final version is -1 meter in 1 second, -2 meters in 2 seconds. So we're going -1 meters per second, the negative sign indicating motion to the left. Okay, we take motion to the left as negative, motion to the right as positive. And again, this is motion just along the x-axis. These are the world line representations of that motion along the x-axis. We're applying the time as the vertical axis here. Okay, what's the big point here? Because that's pretty straightforward, maybe pretty obvious. Well, let's relate the velocity here to the slope of these lines. And again, for those of you who haven't had math recently, don't worry, we're not going to do too much with slope. You may way back in your memory someplace. It may be there, but you haven't done much with it for a long time, so we're not going to go into the details too much of it. But here's what we are going to do. We're saying, okay, velocity is distance divided by time, essentially. So let's look at, we'll do this example right here. Let's look at number 2 here. So the distance traveled, say, from here to here. That's not a very straight line. So there's the distance traveled, and here's the time. Okay, so essentially, dropping things today. Essentially what we're doing is distance traveled is 2 divided by the time 1. Again, if you depending on how much algebra and the like you remember, sometimes we call this the run. Okay, the run here, and we call this the rise. Sort of intuitive, the rise, how far you've risen in a given, over that given distance. So if you have a distance of 2 for the run there, getting all the way over to 4, and the rise is 1. So run is a horizontal distance, rise is a vertical distance. Run on our space-time plot represents x distance, how far it's gone along the x-axis. Rise represents distance, in a sense, in time, how much time has elapsed. So we can say that on our space-time diagram, velocity equals, remember, velocity is distance divided by time. Velocity is run divided by rise. Is run divided by rise. Okay, so if I didn't have these numbers here, and I wanted to calculate the velocity of any given world line here, or really the object, which the world line represents, its motion, I just pick 2 points, and I calculate, okay, how far has it gone? Run. How long did it take? The rise, and that's the velocity for me. You might say, okay, well, that's, again, not too complicated or complex or anything. You're just stating almost the obvious here. But let's look at this in terms of the slope of the lines. And for our purposes, the slope of the line is whether it's sloping sort of downward or sloping upward. Okay, so it's the angle of the line compared to the x-axis or the time axis here. So clearly we can see number 2 has a higher velocity because you're getting more run for a given amount of rise. You're covering more ground for each second that you're going here. And number 3 has the least amount because in 1 second you're only going half a meter, whereas for number 2, in 1 second you're going 2 meters there. So what we can say in general is that when the slope of a line, and the steeper the line is, the higher the slope, we say, and we'll get to the exact definition here in just a second, or the semi-exact definition. The steeper the line is, okay, we say this line has more slope, it slopes upwards more than this line. But for the space-time diagram, the line that has a lower slope, this one, represents a higher velocity than this one. And this will be a key point to remember in some of our later episodes when we talk about special theory of relativity and do a few more space-time diagrams and things like that. Okay? So the lower the slope, the smaller the slope, the less the steepness of a line really represents more velocity because you're covering more ground in a shorter amount of time. Whereas if you have a steep slope, you're covering a short amount of ground in a longer period of time, so the velocity is less. And just to remind you, the official definition, or say the first definition of slope you probably learn, is that the slope of a line equals rise over run. Okay? So it's a measure of the steepness of a line. So it's how far does it rise within a given run. So what's its y value for a given x value? If you have a large difference in y for a small difference in x, you have big difference in the rise. A big rise over a relatively short run gives you a larger number for the slope and a steeper line. Okay? But velocity, we can see here then, is inversely related on a space-time diagram to the slope. steeper slope, like number 3 has the steepest slope here, but it represents the slowest velocity of our examples. Whereas number 2 has the lowest slope, and it represents the faster velocity. Again, it's nothing profound here, just because we're measuring the run here, how far it's traveled x in a given amount of time. So it travels a long distance in a given amount of time, like a second. It just means it's going faster. That's all we're really saying. But again, the concept here is to recognize that steeper slope means lower velocity, smaller slope, lower slope, as it were, less steep of a line, higher velocity. And then this one just means we've got a velocity going in the other direction. So these lines have positive slope because the rise and run are both positive values that run that way and the rise up. This one actually has a negative slope because it has a negative positive rise but a negative run there. And again, we're not going to get into all the niceties of that, but I want you to remember the concept of just being able to look at a picture for a space-time diagram and see a given world line, which will be, for our cases, straight lines, because we'll be doing constant velocity situations, and recognize, oh, this represents a slower velocity than this one, even though this is a steeper slope. And then one more thing here. We talked about these as being 4 different runs for a spaceship. We could also represent them as 4 spaceships all taking off at the same time from our origin. And spaceship number 1 follows that path along the x-axis. Spaceship number 2 goes faster. Spaceship number 3 goes slower. And then spaceship number 4 actually goes off in the other direction. And so again, if you use sort of the animation principle that at x equals 0, that's what it looks like. They're all at 0. At x equals 1 here, if we took a snapshot of the whole x-axis, these would be the locations of our 4 ships. This is one going that way, and this is number 3, number 1, number 2. And then take another snapshot of the whole x-axis. Where are the locations of our ships at that point? The dots represent them, and then t equals 3 and t equals 4, and so on and so forth. Okay, so good to just play around with this a little bit, space-time diagrams, get a feel for what's going on, make up your own little numbers there and do some plots and things like that. And just that the writing down of things, hopefully we'll get it to stick in your brain a little bit more. So moving on, some of the next topics we'll be covering in the video clips. A big topic is the concept of frames of reference. And then we'll move on to something called the Galilean transformation. Again, this is laying the foundations for some of the key things we'll be doing in the special theory of relativity in weeks to come.